Okay, hello everyone. Welcome for today's quantum space-time seminar. Today we have Hofie Hannesdottir from IAS, and she's going to tell us about what can be measured asymptotically. Over to you, Hofie.
Well, thank you so much. And yeah, it's really a pleasure to give this talk titled What Can Be Measured Asymptotically, in collaboration with my fantastic collaborators, Simone Caranjo, Mathieu Giroux, and Sebastian Misera. And the talk is going to be based mostly on this paper from August, and also a little bit on this paper from last October. So let's start with the motivation. So first of all, we want to answer the question in this talk of what can be measured asymptotically. We all know of two observables already that can be measured asymptotically. And here I'm referring to the scattering amplitude and the total cross-section. And we also know that they're even connected in the simple way that the imaginary part of the scattering amplitude is proportional to an amplitude squared here for the total cross-section on the right-hand side. So what we want to ask is, are there any more observables that we can measure at infinity? And are there any similar relations? How are they related to one another? Is there anything similar to this simple relation that holds more generally? So let me iterate on that. So first, we want to answer the question, what is the class of asymptotic observables that can be measured with data at infinite times? We're going to discuss what are their physical interpretations, or which translates into properties of their infrared divergences. And then we're also going to discuss how are these asymptotic observables related to each other. So you're going to see in a couple of slides that answering these three questions almost coincides with the outline of this talk. But let me just keep going with the motivation for one more slide. So what we'll find at the end of this talk is that we will have found a host of asymptotic observables. These will have different physical and analyticity properties, and they'll also have different time delays and infrared divergences. So here I've drawn two of them, actually, that we're going to discuss. On the right, this is the scattering amplitude, and it's drawn actually with time flowing to the left, as we'll discuss a bit later. And here is kind of a space-time picture of what happens during the scattering process, or what could happen. Let's say 1, 1', 2, and 2' are black holes, represented by the red and blue lines, and the graviton is emitted at some point. In this talk, we're also going to discuss this observable on the left, which we call an in expectation value. And the difference between these two is that the left one is kind of on a folded time contour. So these particles go forward and backward in time, and the time shifts at the surface sigma here, which is drawn in orange. And in particular, this means that we'll find that the boundary data is not sufficient to label the observables. In particular, if we just know some incoming and outgoing momenta, that's not going to be sufficient to determine the observable, because we also basically have to know what type of time contour the observable is on, if the time just flows forward, or if we allow for these more general time-folded contours. So here's my outline. We're going to start with establishing what can be measured asymptotically, as we talked about. And one of those observables that we're going to find are going to be precisely the one we found on the previous slide. And it's going to amount to the gravitational waveform as, for example, computed by the Causor or maybe O'Connell or KMOC formalism, if you're familiar with that. If not, don't worry, we'll discuss it extensively in a couple of slides. Next, we're going to talk about LZ-type reduction formulas for these more general observables. And we're going to be led to actually new constraints coming from being able to write down such formulas. So we're going to be led to constraints on for example, the discontinuity structure and the analyticity structure of these observables. In the third part, we're going to elaborate on the physical properties of these asymptotic observables, and in particular discuss the infrared divergences of this observable here, the waveform. And time permitting, we're going to talk about new versions of crossing symmetry which relates these different observables to each other via analytic continuations in the complex plane. But let me stress before I start that I'll be happy to skip this fourth part and take questions midway. If you have any, it's already written in the paper. So yeah, feel free to stop me at any time. All right, so if there are no questions for now, let's start with discussing what is the asymptotic algebra that we assume in quantum field theory. Let me preface before I show you the algebra that we're going to have this algebra whenever the S matrix makes sense. So we're going to be able to write down axioms for the asymptotic algebra whenever the S matrix makes sense. By that, I mean you write down an expression and you can, in principle, compute what it is. So for example, we can discuss pion scattering in 4 dimensions, or perturbative QED or QCD in dimensional regularization. So as I say, I want to emphasize here that we just have to have an expression that we can evaluate, which does not include, for example, unregulated QED or QCD around 4 dimensions. We have to regulate, for example, in dimensional regularization. But up to that, we can use these axioms. So what is the asymptotic algebra that we're assuming? We have an algebra of asymptotic measurements in the far past and far future. So as usual, we have the creation annihilation operators, A dagger and A, and they satisfy these commutation relations as usual, where their commutator is a delta function in all their, for example, spin and flavor indices, which I've labeled here with just a schematic delta 1, 2. And then we have 2 times the energy of one of them. And then this momentum delta functions. I should also say that we use A for the past algebra and B for the future algebra. But in textbooks, you'll often see these as A ins and A outs. But since we're going to be working with basically subscripts and superscripts and daggers, I'm going to call them A's and B's. So A is in the past and B is in the future, just to avoid clutter. And number 2, we're going to assume that these operators act on equivalent Hilbert spaces, and that they're related by a unitary evolution operator that we call the S matrix, or S. So the way to get the future operators is to act with S dagger A, S. That will give us a future B operator from a past A operator. And we also assume that S is unitary. So SS dagger is 1. We assume that there exists a time-invariant vacuum that we call 0, and the vacuum has the properties that it's annihilated by all the annihilation operators, and S acts trivially on the vacuum. So basically, if we start with a vacuum and we evolve to the future, then the vacuum stays the same. The 4th point is a very important point, which we call stability. And this one might be least familiar, so let's go through it. Stability basically says that if I evolve a 1-particle state, then nothing happens to it. So basically, if I act with S on A dagger on the vacuum, then it's the same as A dagger on the vacuum itself. And the intuition is basically that if I have a 1-particle state that's going through, then nothing can happen to it until it interacts with a different state. So that's why it's the assumption of stability. So for example, a particle cannot split into 2 particles at some point. In this talk, we're also going to assume both Fermi statistics, flat space, and Poincare invariance. So you can imagine using these axioms, relaxing some of these assumptions. And that's absolutely fine, except what I'm going to say in this talk is going to rely on these assumptions here.
I have a question.
Yeah.
So usually S is given by e to the minus I Hamiltonian times the time, right? Isn't that correct?
So S here is in the Heisenberg picture. So it would satisfy basically, yeah, it depends on how you write it, but it would satisfy a differential equation. Basically, so that it goes on to the free evolution at asymptotic times and satisfies, as you say, the full evolution in the bulk, basically.
Yeah, so I mean it's a unitary operator. SS dagger equals 1, so I guess it would be some e to the minus I times some Hamiltonian times time, right?
Yeah.
So when it acts on AI dagger, why would it leave it invariant? That's what I
So it's because we're working in the Heisenberg picture. So what you're referring to is basically the Schrödinger picture version of that. So yeah, for example, if there are no interactions, then S would not be e to the I times the free Hamiltonian in this language. It would just be 1. So it's just the difference between whether we allow the states to evolve or we allow the operators to evolve. So here we're working purely in the Heisenberg picture. So there's no explicit time in S.
Okay.
But yeah, that's a good question. Yeah, and I should also say that all of these, even though we'll do some perturbation theory examples later on, then in principle, all of these are axioms that hold non-perturbatively a priori.
Sorry, just a small question.
Yeah.
So if you take AI dagger to be a creation operator that creates, let's say, a muon, then is that forbidden by your axiom number 4? It can't decay into something later on?
Yeah, exactly. So a muon, for example, would not be an asymptotic state, because if we allow it to evolve as we need for the S matrix, if we allow it to evolve for a very, very long time, it will decay.
I see.
Yeah, so that's the idea. I mean, scattering of unstable particles is, to me, a very interesting problem. But as I say, here we're working in this framework where we assume scattering of stable particles.
I see. Okay, thank you.
Yeah, thanks to yeah, these were both very good questions.
Is there a typo in the last equation? Do you have B dagger on right hand side for the first equation?
Where?
In fourth condition, the first equation.
Yeah.
You have B dagger on the right hand side?
No.
Because
so
if you insert S dagger S in front of the vacuum, then S A dagger S dagger should be B, right? Sorry, B dagger.
Yeah, actually, I could have put all of these equations to be equal, precisely from what you're pointing out, because S acting on A dagger is B dagger, but the assumption of stability is really this equation here. It's basically the assumption that a one-particle state in the past and the future are the same if it's not allowed to interact with anything.
Okay.
So this could be a B dagger. That would also be a true equation, but this is really meant to be an A dagger because that's the content of the fourth point. Because what you were saying is basically implied by this equation, basically, right?
Yes.
Yeah. Yeah, so that's precisely why 4 is non-trivial.
Okay.
But yeah, that's a good observation. Thanks. All right, so using this algebra, what can we measure asymptotically? So let's just start writing things down. Let's start writing things that are allowed by this algebra. So one thing we can do is that we can write down A1 dagger, A2 dagger, B3, B4. If we now insert B equals S dagger AS, then what we get here is that if we basically convert both of these B's with this equation and use the equations that we had on the previous slide, that S dagger acts trivially on the vacuum here, then we get that this product here is precisely the S matrix. It's 1, 2 times the S matrix times 3, 4. Where by these bras and kets, I really mean that these are instates in the A basis. So pictorially, we're going to represent this as this blob with the S matrix, and 1, 2 comes in, and 3, 4 goes out. And now you can see why time flows to the left in all diagrams, because we draw time to match on to the conventional operator ordering. So because we're going to be drawing lots of these pictures, and then it got quite confusing if we wanted to have time flow to the right and then operators go to the left. All right, so other things that we can write down at 4 points are, for example, B1 dagger, B2 dagger, A3, A4, which is the S dagger matrix. And then we can write something like A dagger, AA, but we are actually going to set that to 0 because we're going to assume that no incoming particle is exactly forward with any outgoing one. So by that assumption, these last two vanish, and this is actually everything you can write down at 4 points. Every other combination of A's and B's will go to 0, or will just be 0.
I have another question. Like, now you said in the previous slide that S was essentially equal to the identity, right? Because in the Heisenberg picture, I mean, the states don't evolve. Isn't that right?
If it's free. If it's a free theory.
If it's a free theory. So here...
If it's a free theory, then S is just 1.
No, I mean, but in general, you can have interacting theories, right? I mean, so here your S is or is that of an interacting theory? Isn't that right?
Yeah. Here S is that of an interacting theory. Exactly.
Okay.
Okay. So what can we do at 5 points? Let's just play the same game. Let's just start writing down some A's and B's with daggers. So we can always write down the S matrix and the conjugated S matrix. But now we can really start writing down new things. So let's see how they come about. So let's try to unpack these last two, or maybe just the third one. So we can write down A1 dagger, A2 dagger, B3, and then A4, A5. So this is like the expectation value of B3 with 1, 2 on the right here and 4, 5 on the left. And if I now use the relation that B is S dagger AS, I can write this pictorially as this picture on the right here. So by this X, what I've done is that I've inserted a complete set of states. I've inserted it basically here between the S dagger and the A. I can do it over here as well between the A and S, but then A will just annihilate everything except the identity. So we insert this complete set of states X over here. And then we get this, we can write this basically as the S matrix for 1, 2, going to 3, and anything that can happen when we sum over this complete set of states in X. And then X going via the conjugated S matrix to 4 and 5. Does this make sense? This picture on the right here?
The summation over X is only over on-shell particles.
Yes, great point. Thank you. That's a very, very important point, that these are on-shell particles flowing with positive energy. So energy is always positive for every single state in X, and they're all on-shell. So it's really a complete set of states, a complete set of on-shell states. All right. So to summarize, everything that we can write down at 5 points are basically the S dagger for 2 to 3 and 3 to 2. And then we have these expectation values of either B's in states or A in out states, and their conjugates. So there are 8 possible measurements, different measurements at 5 points, if we don't take into account some particle relabeling. So there are 8 measurements types. And this just grows and grows. So at 6 points, we can start having even more things. So we can have, for example, scattering amplitudes. We can always have scattering amplitudes. Now we can start having something like inclusive cross-sections or inclusive particle number, where instead of having just one A or B, then we have something that's quadratic here on the X cut. And then we can start having, for example, out-of-time ordered correlators. So out-of-time ordered correlators are basically maximal scramblings of A's and B's. More generally, we can count how many asymptotic observables we have. We can count the number of distinct measurement types. We're going to call them T. So at endpoints, we can work out that the distinct measurement types satisfy a recursion relation, like this one. So basically what we're doing here is just that we're allowing for any general A daggers, K1 of them, where K1 is greater than or equal to 2. And then we allow for some K2As, K3A daggers, etc., etc. So the number of measurements grows exponentially with the number of points, which is maybe not surprising because we're scrambling the A's and B's in all different ways. So the number is exponential. But the interesting thing is that the scattering amplitudes, which grow linearly in n, form only a small subset of asymptotic observables. So a measure is 0 asymptotically as we go to a large number of points.
Right. Hofie, you're probably going to get to this, but if you take the simplest non-S matrix type of observable, maybe the 5-point guy you had 2 slides ago, could you say how you would experiment? What experimental protocol you would have to measure?
Yes, perfect. That was my next slide, actually. So let's discuss it. Absolutely. So what is the physical interpretation of all of these observables? We all know the scattering amplitudes, so I'm not going to discuss those. But let's discuss, for example, this in an observable. This 1, 2, measuring B3 and 4, 5 in. So the interesting thing is that this observable is not a random one. It's actually the expectation value of electromagnetic field in a scattering experiment. Or it could be, for example, the gravitational waveform as detected by a gravitational wave detector like LIGO, Virgo, and Kagra. And let me try to explain that. Actually, let me go to a picture to try to explain it better. I think I have a picture. Yeah, here. So this is this type of in an observable. So this could, for example, be what goes into the gravitational waveform. So the intuition for this is that we have some black holes in the past, and they will scatter off of each other. And we measure a graviton on Earth. So this H here on the orange cut is supposed to be in the future. So that's what we measure. But the problem is that we don't have a detector that covers the whole universe, right? So we don't know what else happened during the scattering of the 2 black holes. We just know that there were 2 black holes that were incoming. And then lots of stuff might have happened during that scattering. There might have been lots of other gravitons radiated in different directions, but we don't have a way to measure them from Earth. So what we do instead is that we integrate inclusively over everything that could have happened via these states here in X. And then it's an observable, so it's really squared. So it's squared, but it's linear in the field strength. So you can imagine this, if we go back to this expression here, it's really the expectation value of the field strength in the background of some black hole scattering, 1, 2, and 4, 5. And then to get the actual observable, we basically integrate against wave packets that are peaked for this 1, 2, and 4, 5 around the positions of the black holes, the incoming black holes. So whether you work in electrodynamics or in gravity, this would be something like, the expectation value of the field in the background of a scattering.
So 1, 2, and 4, 5 are... So 1, 2 is the initial momenta of the black holes, and 4, 5 are the final momenta. So 4,
5 are also the initial momenta. So it's like a squared. It's like a squared amplitude. Since it's an observable, it's the expectation value of, as I say, the field, which is this B3 operator, in some in state, basically. So it's the expectation value of the future measurement in the past state.
I see. So 4, 5 is the same. Is the Bragg order is the same state as 1, 2?
Yeah. So what we do is basically that we compute these for general in momenta space for general momenta for 1, 2, and 4, 5. Mm-hmm. Then to extract the actual waveform, let's say we wanted to do this for LIGO, then what we would do is that we would integrate basically against wave packets that were peaked around the classical momenta of the black holes. So ultimately, we will set those peaks of the momenta to be the same for, let's say, 1, 4 and 2, 5.
I see.
And then the last,
Sorry, so you have a more general observable, but then you process it to get this physical thing. Yes.
Exactly. So this is the ingredient that goes into it. And as I say, if you're familiar with the Coser or maybe O'Connell formalism, then this is precisely what's computed there. So the idea is basically to use quantum field theory to extract classical observables, and this is the ingredient that comes into it. But yeah, what we have left to do is two things. We have to, first of all, convolve with wave packets that are peaked around the classical momentum of the black holes. And then we have to Fourier transform to position space to get the actual displacement of the detectors. Then we have to do one Fourier transform, basically.
Sorry, one quick question. Sorry to interrupt so much, but
no worries.
In the case that 1, 2, and 4, 5 were the same, is this the thing that that condensed matter people routinely compute? I mean, the thing that is generated by.
Yes, this is like a Schwinger-Keldysh. Yes, Schwinger-Keldysh formalism observable. Exactly.
Okay.
So we're going to come to that interpretation as well in just a few slides.
Okay, thank you.
Yeah, you're welcome.
Is there any physical interpretation of the observable when the momenta of 4, 5 are different from that of 1, 2?
Yeah, I guess you could. Yeah, that's a good question. I can't come up with anything good immediately, but yeah, it would be an expectation value in two different states, maybe some cross term of, yeah, it could be a cross term, for example, in some computation, I guess. But usually, yeah, we would put an expectation value of the same in state, right?
Okay. Thanks.
Yeah, you're welcome. So
I have a little question. So
yeah.
If you have more than one fold in your time contour, then also you have some interpretation in terms of some experimental setup, like, you know, in you have only one, but you, in principle, yeah,
that's an excellent question. And I don't have a good answer. I haven't come up with a useful observable that we can directly measure on many time folds. But let me just say that these out-of-time ordered correlators, they can be used as a measure of chaos in some systems. So that's these papers from Schenker, Stanford, for example, Maldaceno, Schenker, and Stanford from 2013 and 2015. So I think there is there's definitely physical content in them, but I find it hard to imagine how we would measure something that's on more than 2 time folds.
Thank you.
So yeah, you're welcome.
Because at least the way I understand them, the out-of-time ordered correlator that they study in quantum mechanical systems, it gets mapped to the Regge limit of an ordinary scattering amplitude, because the time that they use is the boost time. So the translation sets everything in time ordering. So that's what I thought, that their out-of-time observable, when translated into this, would map to ordinary scattering amplitude in some limit.
In some limit, yeah, exactly. So as I say, they definitely do contain physical information.
Yeah, no, but I'm saying the top line of this slide, not the bottom line of the slide. Maybe bottom line of the slide also has some other interpretation.
Yeah, as I say, yeah, I guess my only comment was just that since we live kind of naturally on one time fold and we compute expectation values, then as I say, it's hard to imagine measuring something at different, something that goes forward and backward in time many times. But they can definitely be useful.
Thanks.
You're welcome. All right, so the takeaway points from this first part is that the scattering amplitude is actually only one of exponentially many asymptotic observables, and they're physical and they can be measured and computed, at least in principle, at least some of them. So in this talk, in the rest of this talk, we'll talk about efficient computations and physical properties of scattering amplitudes and observables. And then we'll relate asymptotic observables to one another via analytic continuations if we get to it in part 4. So as I said, we're done with part 1, discussing what can be measured asymptotically. Next, we'll go on to talk about LZ-type reduction formulas before we discuss physical properties of asymptotic observables. So in fact, we'll talk about 3 ways of computing asymptotic observables. First, we'll talk about how to expand them out in terms of basically ordinary scattering amplitudes and cut amplitudes. So everything reduces basically to a computation of scattering amplitudes or scattering amplitudes integrated over some phase space. But that's actually a little bit not quite, I think, what we want to do more generally, because we've just found that these observables kind of are all in a way on the same footing. They just live on different time contours. So it's actually more efficient, and it highlights the physics to use 2 or 3, either the generalized LZ formula or the analytic continuations. So we're going to talk about basically this first point first. That will be fairly brief, but then we'll spend some time, talking about the generalized LZ formula. Okay, so the first way to compute these asymptotic observables. Yeah.
Sorry to interrupt. So, but from point 1, do I understand that there is no new information in principle in these new observables?
I think there definitely is new information, but we can just reduce the computation basically to a computation of amplitudes, and as I say, some products of amplitudes integrated over phase space, almost like the pictures that we drew before. But I think that definitely doesn't mean that there's not more information, because especially the integrations over phase space can change the properties a lot.
Yeah, at the practical level. But if I were to hand you the full S matrix, you could compute all of the other observables. So in principle, there's no new information. Is this right?
In principle, in principle, everything is built out of the S matrix. Yeah.
Okay, thank you.
All right. So so that's the first thing we will do. We will break up observables into amplitudes and cuts. And let me just emphasize, first of all, that when we draw these lines, IM here is really a connected amplitude. So it means that, for example, these two here are different. So sometimes we break the S matrix basically into 1 plus I times the transfer matrix, or what I've denoted here as I times M. But that's not really going to be useful for us, because we want to separate out basically the different contribution of what's connected and what's not connected. So when we assume that our kinematics is not forward, then disconnected diagrams do not have support. But everything in this sum is actually going to be important for us. So if we were just computing the S matrix itself, then all of these other terms would vanish. Basically, as I say, because we assume that none of the incoming particles are exactly forward to any of the outgoing ones. So something like this cannot happen. But when we're computing these more general observables, then we're basically excluding that anything here on the far right, 1, 2, and 3, is forward to anything on the far left, which here is 4 and 5. So for example, this we would set to 0, because 3 cannot be exactly forward to 4. But we would include something like this one here, where basically one of the particles after the cut just goes along. It doesn't interact with anything, but that's fine, because it interacted with something here when coming from 1 and 2. So that's why it's a bit different for us than what people usually do for the S matrix, because we really have to include all of these forward terms in the expansion. So the result is basically that every asymptotic observable that we can write as these strings of S's in S stagger becomes a sum with familiar LZ or phi. So we're really expanding, for example, here. Let's look at what we can do. So for this 1, 2 to 1 prime, 2 prime H process, what we can do is that first we can take basically this S stagger to be trivial. So S stagger is 1 plus some something connected. So we can take just the one part of this S stagger and take S to be basically fully connected. So then we just get the usual scattering amplitude for black hole to graviton black hole. But now we can do something else as well. We can take this S stagger to be interacting. So we get minus IM dagger over here. And we also take S to be interacting. S can actually never be 1, because that would, because we're creating a graviton here, so we can't have a purely forward diagram. So these are the 2 terms that we need to compute this observable here. So this would be the way to do it, basically by expanding everything out in terms of amplitudes. And recall that this X is a complete set of states, and we integrate inclusively over phase space.
I have a question.
Mm-hmm.
Like one of the black holes could spontaneously emit a graviton, right? So without interacting with the other, isn't that possible?
Yes, it could. Yeah, it could basically emit it before interacting.
So you could still have you could still have the identity on the right-hand side in the last diagram instead of just
on the right-hand side. So if a black hole emits a graviton, that's not the identity, right? Because something happened to it.
In the sense that it doesn't interact with the other black hole.
But it interacts with something. It emits a graviton, right? So one means that if we go back to the previous line, one is really this term here. It means that nothing interacts with anything else. So a black hole emitting a graviton would be an interaction.
I see. But okay, fine.
Sorry, I didn't quite understand this first term in the line. Yeah.
Yeah. Okay.
How is it contain that term also?
Yeah. So maybe let's go back to this previous slide again. So imagine now that this is the S dagger blob from the next slide, basically. So basically what we have to do is that this S dagger blob, it contains the connected amplitude, but it also contains this one term, the term where everything just goes forward. And the reason why we have to keep it is basically because the full diagram has to be overall connected by the argument that an experiment in Andromeda does not affect experiments on Earth, right? But here, since basically, since we have this S and S dagger, then this S dagger could just be one and everything just goes through. The black holes don't interact with anything. So X would just be the same as 1' and 2'.
Okay.
And that's what gives this term on the left here.
Right, okay. Thank you.
But it can't happen on the other side precisely because of this reason that there's a different particle in the final state, so it can't be just a forward diagram.
In the second diagram, does it also include a forward diagram where the lower black hole just goes through?
In principle, that would be possible. So it depends.
So it's just the graviton emitted from the first black
hole. I guess it depends on basically whether we take those to be stable or not. Here, we usually take these to be stable when we model these in quantum field theory. So then something needs to happen. There needs to be an interaction between the two black holes. In this particular case, but yeah, in general, if we had some different process, and especially if we had more incoming particles, then we absolutely would need to include some partially connected diagrams like this. But it so happens that here it doesn't happen by the stability assumption.
Okay, thank you.
Can I go back to this LIGO kind of setup once more? I mean, in the sense that suppose that you have some inelastic collision of the two black holes, like a merger. So then the final state of the black hole will be just one black hole. So you can, and what you are measuring, of course, is again the same thing. It's the expectation value of the gravitational field at your, LIGO lab. So, yeah, can you take that into account? Like you have one asymptotic state rather than two.
Unfortunately, right now there is a lot of work on this being done right now. Basically, trying to relate these scattering computations, where the black holes scatter and we have two black holes in the final state, to something like you mentioned, like an inelastic process where there's a merging process and we end up with just one black hole. The idea is that maybe there's some analytic continuation that gets you from the scattering state to the bound state, similar to the intuition in quantum mechanics. But right now, unfortunately, people do not know how to do it. And if we figure out how to do that, then all of these methods would be so much more useful for LIGO, right? But there is still maybe a hope that these scattering waveforms may or may not be measured in the future. And
I see.
They may or may not be there in the data already, as far as I understand, but it's a super interesting question. And hopefully, it would be a dream if there was an analytic continuation between the two.
Okay, thank you.
Yeah, you're welcome.
Sorry, but just to follow up on that, in principle, I mean, you may not now be able to compute it, but in principle, that X includes everything that could form, including this one black hole.
Yeah. In principle, yeah. If it's a valid state, then in principle it would include it.
Yeah. Okay. Thank you.
All right. So let's get to I wanted to mention, we're going to come back to this later, but I just wanted to give you an example of Feynman diagrams, which we could compute in this formalism. So again, everything is set up non-perturbatively, but we're allowed to expand in perturbation theory if we want to do those calculations. So we can do that here, for example, and this is something that there's been a lot of interest in computing these recently, basically the one loop contributions to this gravitational waveform in the classical or in the iconal approximation. So what I want to show you, which is some example diagrams and what would be the cuts that would be allowed, basically which diagrams we need to take into account and which ones we don't. So the topologies that we're going to be looking at are these box diagrams where a graviton is emitted. So things that would not be part of this observable that we call X3, basically the expectation value of this particle that we call 3. It would not include these diagrams because, for example, for this one, the graviton has to be emitted before the orange cut. So this is just not there in this, it's not included in this blob picture up here. Same with this one and this one. The graviton really has to be emitted first. So let's go down here. Then we could imagine something like this diagram here in the middle, or actually all of these have the graviton emitted before the orange cut. But these actually all vanish in on-shell kinematics. So these would in principle be allowed cuts, but they just happen to be 0. So our observable includes these. These are parts of our blob pattern, but they just happen to be 0. Our observable does not include, for example, these ones where we cut the 2 heavy lines. So these solid lines are supposed to be the black holes, and the wavy ones are the graviton corrections, or the gravitons that correct them. We always have to cut all the way through. As we were discussing earlier, all the states on the cut really have to be on-shell states with energy going forward. So if we do a cut on this black hole here and this black hole here, it's not a cut that goes through in the sense that we can draw, this is our final state in this case, with all the particles being on-shell. So if we cut some random particles, these are not unitary cuts. So really the diagrams that we have to include are these 5 down here. So the 4 first ones are actually all scattering amplitudes. They're basically setting this S dagger to 1. So we've drawn the orange cut here close to the final state, but there's really like a 1 that evolves these trivially. But the last one is an interesting one. The last one is a genuinely new one for this observable. So we cut through the black holes over here, but the graviton is emitted before the cut. So this is an allowed unitarity cut. Everything that crosses the orange line is on shell with energy flowing forward. And this is something we have to compute in addition to basically these 4 scattering amplitudes if we want to compute this observable. So that concludes this first way of computing observables, which is to sum over amplitudes and cuts.
Sorry, Hofie,
so let me pause.
Why is the third set? Why the diagrams in the third set vanish?
The third set here?
Yeah.
Oh, it's basically just because if you try to track these kinematically, so these, for example, are both on shell. Can you see my cursor over here? Okay. So let's look at this on-shell process here. There is an on-shell black hole with a mass. It emits a graviton that then splits into 2 other ones. But this one has the same mass as this one's the same black hole. It has the same mass. So this is just not an allowed on-shell process. We can't have one. Sorry?
Why does it have the same mass?
Basically because we're doing this in this iconal approximation, where we model the black hole as like scalar, with the black hole is not losing any mass when it emits the gravitons. It's a stable, yeah.
So basically you don't want your cut to cut the intermediate black hole?
I just want all of these to be allowed on-shell processes. As
So
I say,
how about the
this,
last diagram in the last set, fourth set?
This one here?
Yeah, so there also the cut is happening on the black hole that has emitted this graviton, right?
Yes, but here there is an exchange of momenta between these two black holes. So this is like a 5-point tree-level scattering process on the right, which is different from like a black hole splitting into a bunch of particles. Does it make sense?
I don't quite see the difference between this and I mean the difference that make it vanish. The first diagram of the third set and the last diagram of the fourth set, for example.
Yeah. So okay. So here, if we view this part of the process separately.
Oh, sorry, these guys are on shell. Okay, sorry, yeah.
They are all on shell.
Right.
Yeah.
Sorry, the graviton.
These are all...
The cut also cuts the graviton, which is on shell, but here
exactly.
Thank you.
Exactly. So over here, this is just a scattering process, as I say,
okay.
Which is different from this one here, which would be like a decay process. But since the particle is stable, then that cannot happen.
Yeah. Okay. Thank you.
I have a naive question.
Yeah.
So when you are saying that the black hole emits a graviton and it doesn't change its mass, but the graviton carries away some energy, right?
Yeah, so that's precisely why we need these scattering processes. So it's not like Hawking radiation or something. It's really, we have two black holes and they scatter off of each other. And that's how it's modeled in quantum field theory, basically, that we just have a scalar, a heavy scalar.
Okay.
Hi, I have a really silly question, perhaps, but like, how is this different from your three-particle cut interpretation? Like the ones which vanish here, the ones which you're saying are vanishing. In the gravitational wave, in these derivations from scattering amplitudes, we normally have these from three-particle cuts, right? With an exchange graviton in the middle.
I'm not sure exactly what you mean.
So you would have a 5-point amplitude, and you have a three-particle cut with the exchanges, and you integrate over them, and those give you classical contributions. But here it seems like a similar diagram is not giving you a classical contribution. Is this correct, or am I misinterpreting something?
I'm not sure exactly what you're referring to, but let me just say that these are precisely the diagrams that are computed for this observable. As I say, what they also do is that they use generalized unitarity in some intermediate steps where you have some cuts which are not on shell, which is very different. No, sorry, not unitarity cuts is what I wanted to say. So you put the particles on shell, but you don't need to cut through the whole diagram, and you use it basically to match your computations onto a basis, etc. But here, these are really the diagrams that we start with, and that's the same diagrams as they start with. I'm not sure I understood exactly the question, but
I might not have understood something as well. I'm sorry. It's fine. I think I got it. So
So this is just
is it an issue about exchanges between crossed ladders being a problem?
Between what, sorry?
Exchanges between crossed ladders in the iconal approximation, is that a problem?
So we can have these crossed ladders. That's totally fine. The only thing that cannot happen for the crossed ladders is that we cannot have basically cuts that don't vanish.
Okay.
Yeah.
Okay, I think I got that. Okay, thank you.
Awesome, thank you. All right, so if there are no more questions, let me in the last 10 minutes maybe go to the second method for computing the generalized the asymptotic observables. Yeah.
Just to say that we are very flexible about time, so if you have the energy, you don't need.
All right, that's good to know. That's great. I'll not rush through then, at least. Thanks. But this is great. I really like how many questions there are, so please keep interrupting me. I would much rather have more questions and get through less material. Yeah, okay, so let's keep going. Let's now talk about generalized LZ. What we did in the previous slides was basically that we in a way did too much work, because we unfolded everything in terms of scattering amplitudes and cuts. And in principle, if you have a general observables, you would have many, many, many terms of these. What's going to be much more efficient for us is to just start from the starting point that these observables are not inherently any different from scattering amplitudes, except just they're on a different time contour. So we're just going to derive a reduction formula, an LSZ reduction formula for these observables directly. So let me first talk about basically how we might imagine doing that, how we might imagine going to these different bases of different time orderings. So the physical setup that we've been talking about is that we measure the field of a graviton in the background of black hole scattering. So again, time goes to the left over here from 1 to emitting a graviton to the state X. This cut is really in the far future, where we measure the graviton and sum and integrate over everything else. And then since it's an in observable, we can think about time as going to the right on the left here in the S-stagger blob, basically. So this is the physical setup, that the graviton is measured in the far future, but everything else is in the far past. So using nonlinear response theory, and this I'm not going to go through in detail, but it's in our paper, we can work out that this observable is precisely represented by the retarded function. So the retarded function is in spirit similar to the time-ordered function, which we use for scattering amplitude, except it basically orders things differently with time. So the retarded function is defined making one field special. So, for example, in this case, the retarded function of 2 of 5152, so we're making 2 special, is the commutator of 1 and 2. And then we impose that 2 is in the future of 1. And this is basically what we iterate. So if we have the retarded function making 3 special, making 3 in the future, of 1, 2, and 3, then we basically get these nested commutators, putting 3 in the future of 2. So this commutator is the innermost one, and then 2 in the future of 1. And then we sum over the 1 to 2. But again, 3 is special. 3 is always in the future of both 1 and 2. But then we kind of scan over all different time orderings of 1 and 2. So that's precisely the physical setup, kind of the physical time contour for this graviton here. The graviton is in the future, but all of the other on-shell states are in the past. All of the black holes are in the past of the graviton. So we can put these different time orderings basically on a Schwinger-Keldysh contour, where these time orderings and the retarded functions are both bases for different operator orderings. So let me mention, because it's easier to...
in your previous slide, you used the word that you have to use this nonlinear response theory. What was the reason for this? That to show that you have to use retarded functions?
Yeah, precisely. It's just what we want to do is to show how the system basically reacts to a perturbation in this way, that where we put the graviton in the future of everyone else. So okay. The reason is it's precisely just what you said, to derive that the correct time contour to use for this observable is this retarded function. That's the only reason why that's what we wanted to derive.
In this particular computation, it's just exactly what condensed matter people do all the time, right?
Yes.
Which is you start in a state, then you turn on some perturbation in the Hamiltonian, and you want to know how that affects an operator.
Exactly. It's just it's precisely just the Schwinger-Keldysh formalism. It's precisely what's used in condensed matter theory. Nothing else different. But what I wanted to introduce here is just this idea of these different operator orderings, basically. So let's say we have, for example, the vacuum, and then a time ordering of A and B, anti-time ordering of C, D, and E, and then a time ordering of F and G. Then we can basically put it on this one contour. And here we're going to need 3 folds. So we're going to start with a fold 1, which is basically this vacuum. And then we hit some operator A, we hit some operator B, and we flow forward in time. So again, forward in time means going to the left. Then we're going to connect here with a tiny imaginary part to the fold 2. And the fold 2 is going to represent this anti-time ordering, where we go backward in time to C, D, and E. And then with the time ordering, we're going to go forward in time again to F and G. And the important point is just that T and R are both bases for different operator orderings. So now what we're going to do is that we're going to derive an LSZ formula, an LSZ-like reduction formula for all of these different bases of time orderings. So if we have an observable, like for example, the waveform, which is represented by a retarded function, then we can just directly apply this LSZ-like formula to it. So what do? We just start exactly like in the textbooks. So this slide is more or less exactly like in textbooks. So we define the creation annihilation operators, A dagger and B dagger and B and A, as surface terms of currents. So the observation is that the currents, which are basically some box plus m squared acting on phi, if we take the Fourier transform of these currents and we go on shell, take p squared to minus m squared, then these become surface terms. And then this exponential here will be rapidly oscillating unless we're precisely in the direction where x and p are proportional to each other. So it's natural to label these surface terms here, which occur basically at minus infinity and plus infinity in time. We label them with the momenta p. So this can be taken as basically the definition of the A daggers and B daggers and A's and B's. The important part here is that there will be a time integral here, which runs from minus infinity to plus infinity. So actually, when we define these surface terms here, we really need one in the past and one in the future. So we need an A dagger in the past and B dagger in the future. And same here, we need an A and B. And then depending on whether they're incoming or outgoing, they will be daggered or not. But let me emphasize that it's very important for us to write down both the operator in the past and the future. Sometimes you'll see in textbooks, basically that you'll see the B dagger being dropped and the A being dropped. And the reason for that is that you don't need them if you use the time-ordered product. For the time-ordered product, you really just need the A dagger and B. But to me, it's both clearer that these come from surface terms, so you need the past and the future ones. But also, they are going to be important for us, so we cannot drop them.
I have a question.
Mm-hmm.
You go back to the previous slide. Yeah. So when you have p square equals minus m square, this jx simply vanishes, right? Because it is given by minus del x square plus m square. So if you just go on shell, it would vanish.
Yeah, so on shell, this becomes precisely a surface term here. If you just do this, if you take this limit, this becomes a surface term.
No, I mean not only a surface term, it would vanish because then the minus del x square plus m square would give 0 acting on phi x.
So for the S matrix, we add this term basically to be on the pole, right? There will be some pole produced that we cancel with this box plus m squared.
Sorry?
It's just the standard textbook story. As I say, we have some time-ordered correlation function. It has some poles at p squared equals minus m squared, and then we act with box plus m squared to sit on that pole.
No, I mean, if you have defined jx to be this particular function, and then you have jp, you're taking the Fourier transform of that, jp equals this. Now, on this particular expression, dx e to the minus I p dot x jx, when you put p square equals minus m square, since jx...
It becomes this right-hand side here. That's what it becomes. It becomes a total derivative.
That's what I'm not getting, because jx, when you put p square equals minus m square, this jx on the left-hand side simply vanishes. And then you have nothing left.
So this is just, I mean, you can just plug this in. There's just a calculation that it's basically just, you have the derivative here, act out here. on this one here. So this is a computation you can do by integration by parts, basically.
Yeah, you can do it by integration by parts, but if you don't do the integration by parts, I mean, you can simply I mean, this Jx, since Jx is just minus box plus m square acting on the phi x.
As she said, I mean, it's just the usual stripping off of poles. Correlation functions involving this phi have infinities. These zeros cancel those infinities, you get something finite.
No, when you act this on correlators, I can imagine you can have.
I think that's the spirit of what's going on.
Because when you act on correlators, you have 1 by p square plus m square, and then 1 by p square plus m square cancels with the p square plus m square outside. But when you just have phi of x, I don't see how.
I think the point that Hofie is trying to make is that this box plus m squared is not zero everywhere, right? Because there are interactions turned on, and it's only true at infinity that it like this p squared plus m squared is zero. So that's why you have to make it a boundary term first. Yeah, sorry, please go ahead.
Exactly. That's precisely why it becomes a boundary term. But again, this is just something that it's 3 lines that I didn't write out to basically show that this left-hand side is equal to the right-hand side on shell.
I think we can move on. This is just the Ellipsis textbook, as you said.
All right. So now the interesting thing is that the scattering amplitude, actually, we can define it, and this is going to be important for us, either as a time-ordered product or as a retarded product. So let's go through it here. If we now Fourier transform to momentum space, so this is the scattering amplitude in momentum space, and what this time ordering here is going to do, if we act with the time ordering on these currents, so if we write down our definition, the J of P4 is going to be B4 minus A4, etc., this string here. So what happens? The time ordering basically shoves all the B's to the left of all the A's. So we'll have a term here that goes like B4, B3, A2 dagger, and A1 dagger acting on 0, which is precisely the scattering amplitude. And I'm claiming here between those 2 lines that everything else basically vanishes. Because, for example, let's take this A4 term. This A4 term would always be put to the right of all the B's. So this A4 term will always annihilate the vacuum. So this is why in textbooks, you'll sometimes just see, if we go back 1 slide, you'll just see this A dagger and B, basically because for the time order product, we don't need them. They'll always be shoved either to the left and to the right where they annihilate things. So really the only term we're left with here is this one, A1 dagger, A2 dagger, B3, B4, which is scattering amplitude, and this is supposed to be the momentum conserving delta function shorthand. Okay, but we can also write the same object in a different way. So let me just write this expression here first, and then we'll see why it's the same. So I can write it as a retarded product of 3 being in the future of 2 of these 2 currents, JP3 and JP2. So let's write the definitions that we had before. Now the shoving of A's and B's is going to be a bit different, because now 3 is always going to be put in the future of A. Instead of ordering them in time, 3 is always in the future. 3 is always in the future of 2. So actually the same thing happens here, that basically the only term that survives out of this product here is B3 A2 dagger. So we get the scattering amplitude written in 2 different ways. And let me emphasize that the different time orderings are not just different bases or some tricks. They really need to lead to new formulas and new predictions. So we'll start with presenting 2 arguments. The first one will be anticipating crossing, and the second will be a discontinuity formula. So the reason why I've talked so much about retarded product is actually because in proofs of analyticity properties of scattering amplitudes from the 1960s, the retarded products are really the star of the show. So basically the game is that intuitively a theta function in position space cuts off a position space integral and opens up a region of analyticity in momentum space. So the time-ordered correlation function is actually horrendous for proving any analyticity properties, because we have e to the ip dot x floating around everywhere. And this e to the ip dot x is going to have some exponential enhancement in some directions because we're integrating over all x. But if we instead use the retarded product, then we're cutting off the x integral. For example, here, we're saying that 3 always has to be in the future of 2. So we get some theta function in our s integral, and that opens up some region of analyticity in our momentum, momenta. So this is the starting point of proving crossing symmetry. It's basically noting that the retarded product of P3 and P2 that we wrote down before, basically sandwiched between this A1 dagger acting on the vacuum and B4 acting on the vacuum. Basically, if we take the energy of P3 to be either positive or negative, then we either get the scattering amplitude if the energy of P3 is positive, or we get the conjugated scattering amplitude if the energy of P3 is negative. And these are the two functions that can be related via analytic continuations. It's a scattering amplitude in one channel, 1, 2 to 3, 4, and a conjugated scattering amplitude in a different channel, 1, 3 going to 2, 4. Here I have not proven for you crossing or analyticity. The only thing I've shown you is that the retarded product evaluates to two different functions, one in this channel where P30 is greater than 0, and another one in this channel where P30 is less than 0. But it remains to show that there exists a path of analytic continuation between them, and that are these order 200-page proofs from the 1960s is actually showing that these two are not just different evaluations of the retarded product, but really that we can analytically continue the retarded product. And in the crossing part of our work, or in our latter paper from this October, then basically what we noticed is that we can replace this argument in a similar way for higher point amplitudes. So we can take A or D here to be basically any set of creation or annihilation operators. So this relation, an analogous relation using the retarded product, is our starting point for understanding crossing symmetry. So let's show how that works out. Basically, let's try putting the set A to be A1 dagger and the set D to be B5, B4. And let's write down the retarded product in this case, where 3 is in the future. So we get A1 dagger, A2 dagger, B3, B4, B5, which is the scattering amplitude in one channel. But if we use the relation from before, basically what the retarded product is in a different channel, where 1, 3 goes to 2, 4, 5, then we get this A2, B3 dagger. So basically what this amounts to is that we get a scattering amplitude in one channel, and then we get this inclusive observable or in an observable in a different channel. And these are the two that can be related via analytic continuations, as we showed in the second paper that I'm not going to talk, at least not much about today. But yeah, I just wanted to mention this, since we're going through this LSZ formula, that this is really the trick. The trick is to use this retarded product, use this rewriting of scattering amplitudes, rewriting of observables with this LSZ formula, and then we gain this mileage that we open up some region of analyticity. And yeah, we'll revisit this point soon. Before we do so, let me say that we can also keep playing around with these different bases. So for example, we can write this object here. This is chosen at this point quite randomly, but it's just to show you an example of what we can do. So we can write, for example, this cut here as this product of retarded products in this way. And now we're going to consider basically translating x3 and x4 jointly with a parameter xi. So if we were to compute the discontinuity in S34, we would basically want to take xi to infinity. But xi actually cannot reach infinity. And the reason for that is that 3 always has to be basically in the future of 4. So we can't do this joint translation and reach infinity with xi. So this predicts that the discontinuity in S34 of the cut in the 4-5 channel is 0. So if you're familiar, for example, with the Steinmer relations, this looks very analogous to that. If not, then just take this as one type of formula that we can derive on analytic constraints. But what I wanted to say is that we haven't quite explored the extent of this. We just had these couple of examples, which we noticed, but I think it will be interesting to really explore what are the different types of bases and different types of constraints that we can derive, playing around with these different time orderings. So that concludes actually part 2. And if everyone is still okay with time, part 3 is actually quite short, and I find it quite interesting. So if it's okay with everyone, let me go through that as well. Because now we're going to really talk about the physical properties of these asymptotic observables. So again, I'm going to flash this slide for I think the 3rd or 4th time of how we compute the scattering waveform as an inner expectation value. And we've discussed this extensively now. We can either evaluate this as a generalized LSZ, or we can expand it out as amplitudes and cuts. And we now have a new way of understanding the waveform as this observable on a folded time contour, on a Schwinger-Keldysh time contour. So now I'm going to talk a little bit about the computation and perturbation theory. Basically, what we want to do to extract this classical waveform from quantum field theory is that we want to do an iconal expansion. And yeah, I should say before the references vanish that this is based on this Causal or maybe O'Connell formalism, which is this paper here, which these 2 papers really taught us how to basically extract classical observables from quantum field theory. But then this particular diagram, this one loop contribution, was computed in these 4 papers from earlier this year, which are all listed here. And as we talked about before, we have to add over these basically 5 diagrams, these 4 diagrams that would be the scattering amplitudes and the cuts. And then to get the classical expansion, we want to expand basically in large values of the masses of the black holes. So again, so I should say if you're familiar, for example, with heavy quark effective theory, then this is exactly the same thing, except applied to this setup. But the important part is actually that we have to expand both the propagators and the delta functions. In principle, we would need to expand them in the heavy mass expansion. So to subleading orders, we basically get these squared propagators and we get these delta prime, these derivatives of the delta function. But actually, we've learned that there's no need to expand term by term. Instead, we could just use our folded time contour and impose boundary conditions to fix which classical observable we're computing. So if you're familiar with the differential equation method of computing scattering amplitudes, this would just correspond to putting different boundary conditions in your differential equation. But that's not quite what I wanted to discuss. You can go through and compute these, and we have some of those computations in our paper. What I rather wanted to discuss was what happens to the infrared divergences and the analytic properties. So this waveform or wave shape or inclusive observable has different analytic properties than the amplitude. So again, we're coming back to this picture where this is the scattering amplitude, 1, 1 prime going to graviton and 2, 2 prime. So on the right, this would be basically 1 and 2 coming in from past infinity. Some particle would emit a graviton, and then we would have 1 prime and 2 prime outgoing. The important part is that if we compute this in quantum field theory, then this propagator here would be a Feynman propagator. It would have the usual Feynman I epsilon prescription. However, here, when we're computing the retarded product, what happens at the level of the calculation, if you go through and you plug in basically sum over these diagrams, including this cut term here, is that effectively this propagator here is no longer the Feynman propagator, but rather the retarded propagator, precisely as required by causality. So in a way, it's just a consistency check that our calculations are really reproducing what we expect from the physics, and they do. The infrared divergence is even more interesting. So actually, when we came to these calculations, the other groups had not included the cut term in their calculations to subleading order. So one of the ways that we noticed that the cut term had to be included is because of this modified infrared divergence of the inclusive observable. And this modified infrared divergence has, basically there are two sources of infrared divergences, which in the classical computation would be two sources of Shapiro time delays. So there's one delay from the graviton escaping the classical gravitational field. So this is very easy to understand. This happens, of course, all the time in quantum field theory, that if we compute something that is basically classically has a long-range force, then we get an infrared divergence. So here the setup is that we have some black hole scattering, and the graviton, if we do our computation in quantum field theory, we take the graviton to be a freely evolving state. But basically, because of the gravitational potential, it will travel on a bent trajectory compared with the free evolution. So that's this part one. There is some delay from the graviton escaping the classical gravitational field. But here, for these infinite observables, there is actually a second source of infrared divergences, or equivalently a second source of Shapiro time delays, which is a delay or advance from the two black holes approaching each other earlier or later than anticipated from classical motion. So let me elaborate on that. Basically, let's say that we start with two black holes in the past, and they're separated by some distance that we call Rn on this figure here. Then imagine this was non-relativistic, then the black holes would approach each other faster than straight trajectories, basically because gravity is attractive. So they would come together earlier than we would have expected if they were just straight lines that would meet basically here. And we draw this actually as a delay, because if you go to high enough velocities, this will actually change from being a delay to an advance. So now we can compute this, and we can compute classically what we expect for these time delays. So for example, we can put these black holes to be some short-shelled black holes, and we can compute these two effects, and they add up. Let me put some labelings here. Basically, this is the red effect. It's a graviton escaping the two black holes.
Sorry,
so we get
I didn't quite understand why is it that you're representing this as a delay when the black holes are coming faster together?
Yeah, good. Let's discuss that again. So, so you're talking about this blue effect here, basically? Yeah, good. Yeah, so that's the new effect. That's the interesting one. Basically, what happens for the Indian observables is that we start with a state in the past. And as I say, if we were computing this classically, we would fix the distance between the two states in the past. So we would say we start with some states that are separated by this Rn.
Yeah.
And then imagine that this is just classical Newtonian gravity. Then these two black holes have an attractive force between them.
Okay.
So in quantum field theory, we're saying they just go along straight lines. That's basically what we're computing, right? We're saying, oh, we have two particles coming in, and before the short distance interaction happens, they just go along their initial velocities, right? Okay. But we know that's not what happens. Even classically, that's not what happens, because of gravity is attractive. So these two black holes will come together earlier than we expect. And actually earlier by a logarithmic amount. So earlier by basically a log in this Rn distance. And if we now go back to quantum field theory, then it's kind of hardwired into our calculation that we always take time and space to infinity, right? We always take time far back. Basically we always go to the past infinity for our initial state. So this log of Rn, if we take Rn to infinity, it translates into a logarithmic infrared divergence in quantum field theory.
No, I just mean that they should meet earlier, right, than later.
Oh, yeah, good. So the earlier...
Here the picture suggests that they're meeting somehow, waiting for each other and meeting later.
Great. So the earlier one is the non-relativistic limit. And if you compute this, you actually see that there's a turnover point. And at some point, it changes from being an advance to a delay. So the delay is what's depicted here.
Why is there a delay in two black holes meeting each other?
I guess the short answer would be that our intuition breaks down when they're traveling very fast. It comes out of the classical computation as well.
Compared to just unaccelerated motion?
Compared to if they were not interacting with each other.
I see. So yeah, I'm not sure. Yeah, still don't understand what kind of situation would they come closer slower than what they would if they were not interacting. Because as you say,
yeah. So as I say, maybe I have this equation here. As I say, at a basic level, it's just a computation. But there is some. Basically, there is some turnaround point where this goes from positive to negative.
Okay.
That's the short answer. Yeah, so it just comes out of the computation. It's the short answer. And our intuition is, I think, for the Newtonian case where it's non-relativistic.
So if this is this that change in time for the sort of the black holes meeting or delta t?
Yeah, exactly. So there's two sources. One of the infrared divergence. Let me actually just write all of these here. So one of the source is basically the graviton escaping the gravitational field, and the other one is the source that's new for the Indian observable because it's not symmetric around the scattering point. We're really fixing boundary conditions in the past, and then because the black holes interact with each other before the scattering occurs, we cannot approximate them as traveling on free trajectories. That's the intuition. Yeah, so here I've highlighted this.
Can I ask two quick questions? So this is still, so are you considering the iconal approximation with corrections to the iconal trajectory? Is that essentially what's going on, or is it something else?
Yes.
Okay, so you're considering fluctuations of these straight line paths. And it's still a weak field approximation about a flat background, or is it, are you assuming like a curved background in general?
Yeah, no. So what happens, as I say, what happens technically is that our scattering amplitude calculations, they don't allow for this bending of the black holes. It's hardwired into our computations that the black holes travel freely and interact in a short distance. This is the same thing as happens in quantum electrodynamics, for example. And the avatar of that is that we're not including this. Basically, we're not including this classically divergent logarithm, or what would be classically divergent if we take this Rn to be infinite, compared with the impact parameter here. And the avatar of that, let me see if I have it here, is precisely this infrared divergence here. So we have a logarithm that represents the infrared divergence, and we can predict and compute that there is this correction term that, because we didn't include that the black holes approach each other faster or slower than expected, then we'll get this extra infrared divergence. And yeah, since we predicted this has actually been computed by the groups that had the papers in February, but I think last time I checked, the revised versions were not out, but they've confirmed that this is precisely what they find for the infrared divergence.
Thank you. So this is like, is this similar to the subleading divergence that we have from, I don't know if you're familiar with it, but you have a logarithmic divergence which shows up in for the soft graviton at the first subleading order, which is of a logarithmic type. Is this similar to that?
This is still Yeah, this is actually still leading order. The only difference is that we're putting things in a folded time contour. So it's not the subleading soft factor, it's just the leading soft factor, but we have to integrate over this different time contour. But yeah, that's a good question. It's still just the leading contribution. All right, so that actually brings me to the end of part 3. So let me actually try to wrap up here because we're already almost half an hour over. Let me just say that the 4th part is basically about relating these different asymptotic observables to each other via crossing symmetry. And again, the paper is out and there's multiple talks online as well. I'm happy to take questions about it. Let me just give you the punchline that crossing symmetry is an amazing fact of quantum field theory. The reason why we like it is that it allows us to use results from previous computations. So for example, crossing symmetry tells us that these two functions should be the same, that E plus E minus annihilation to 2 photons is the same function as Compton scattering. So basically what we've done here is that we've taken the photon and positron and crossed the photon to the initial state and the positron to the final state where it becomes its antiparticle. But just to drive home the point of how crazy this is, let's say we wanted to compute how an apple falls to Earth. Then that's a scattering process between the apple and the Earth. And what crossing symmetry tells us is that we could equivalently compute the process Earth anti-Earth going to apple anti-apple. And if we do that, we know everything that we want to know about how an apple falls to Earth. So the nice thing here is that, let me just say that the crucial result is that in our calculation from before, we now have this 3rd way of computing the waveform, which is to analytically continue the 5-point amplitude, which is a bit crazy one. It's a hard graviton and a black hole going to black hole, anti-black hole. So basically the punchline is that if we start with this scattering process or conjugated scattering process, then the waveform is its analytic continuation in the complex plane. So that brings me to my conclusions. We talked about asymptotic observables as those that we can form with an asymptotic algebra. They're measurable, computable, and have new and interesting analytic properties. And then we talked for a while about different reduction formulas. We did not have much time to talk about new versions of crossing symmetry. But let me just tell you that the punchline is the following, that the S matrix contains a host of asymptotic observables, which are related by analytic continuations between different channels. So with that, let me thank you so much and really thank you for all of your questions. It's been fantastic for me. And yeah, I'm happy to take some more.
Thanks so much, Hofie, for a wonderful talk. Let's all thank Hofie. We had a bunch of questions during the talk, but if there are a few more, maybe we can have them now.
So sorry. Oh, please go on, sir.
Go on.
Yeah. So just you mentioned that you can get these new observables by some analytic continuations of the usual S matrices, right? So I was just wondering, based on the analytic properties of these new observables, is there an alternate way to perhaps directly bootstrap them as well?
Absolutely. And I'm not sure if you're referring to perturbative bootstrap or non-perturbative bootstrap. No matter what you're talking about, I think this is going to be very important for that, especially for the non-perturbative bootstrap, because this is kind of the starting point for the bootstrap of let's say 2 to 3 amplitudes, because we have to basically, in a similar way to how the 2 to 2 bootstrap, I even have a slide about it. The 2 to 2 bootstrap basically assumes analytic properties like this one here, that there is some S channel amplitude over here and some conjugated U channel amplitude over here, and that's kind of built into the ansatz. Before we do anything, we have an ansatz that has this analytic structure. And now we know that this is kind of the, whoops, I went in the wrong direction. I wanted to go back to the conclusions. that this is kind of the starting point for, as I say, the 2 to 3 bootstrap, because we have to know what the basic analytic structure is, and this is what it is. We have these different observables living on the different sides of the axis.
You see, yeah. Okay, thank you.
Yeah, you're welcome.
Sorry, about your LSZ formula, I wanted to check the following. Is it right that to compute your observables, you go on some appropriate time-fold contour?
Yeah.
You put all your insertions either very early in the past or very late in the future, and then strip off poles, and then you get.
Yes.
That's
exactly. Yeah. So the LSZ, it's precisely what you said. Let me just go to the relevant slide. It's basically just using this formula here. It's the content in a way of the LSZ. The content is twofold. It's first of all writing down the correct time contour, and on that time contour inserting these operators as appropriate, and then shuffling terms around so that you get the correct operator ordering, basically.
And inserting those operators is the same as just inserting phi's and then stripping off the poles. Is that right?
Yeah. Exactly. Precisely because of this formula.
Okay, excellent. Okay, I had one more slightly vague question. One could imagine computing these correlation functions on time folds without putting the insertions at very late and very early times. That would not be something you could measure from asymptotic infinity, but anyway, one could imagine computing them. I was wondering whether the analytic continuation properties you told us about, the analytic continuation going from one to the other, whether that it was important that you were putting these things at very early and very late times, or there was a generalization for what you said that would apply even to finite time insertions.
That I wouldn't claim anything about, to be honest, because all of the analytic continuations we do are in momentum space. They do very much everything is so fiddly in the sense that if you change your variables or something, the analytic structure becomes completely different. So the only thing I would claim anything about is what we worked out, which really relies on being in the far past and the far future. I think it's a great question, but as I say, I don't want to claim something about something I haven't worked out. But it does not follow from this for sure. Holds for
I was thinking that.
Yeah.
Sorry, I was thinking that this folded contour is an obvious analytic continuation of Euclidean correlators in position space.
Yeah.
So the analytic continuation you need to do to go from, let's say, Euclidean correlation functions to these time folded in position space is completely obvious, right?
Yeah.
And that would apply also at finite times.
Yeah.
I was wondering whether what you were saying was somehow related to this.
Yeah, so the problem is that, as you're saying, things that are trivial in position space are not necessarily trivial once we go back to, an analytic continuation basically of on-shell observables. And everything is fine off-shell, but what can happen on-shell is lots and lots of different things. And one of the things is that you might have this beautiful off-shell crossing relation. And then as you go on-shell, you have some branch cuts that literally just close up and obstruct the analytic continuation. And we actually have an example of this in our paper. So it's not, as I say, manipulating things off-shell, and in position space, it's non-trivial to go back to the on-shell asymptotic statements or on-shell observable statements. So as I say, I'm very sorry I can't give you a better answer. It's
an excellent answer.
It is what it is. As I say, it's subtle, and it's not trivial that if you can do it off-shell or in position space, that it holds on-shell.
Thank you so much.
Yeah, you're welcome.
So one question for the massive theories, is it this crossing has been established at the level of this Epstein gloss, this paper, this classic paper?
Yeah. Good. So I even have a backup slide on this, but let me just go to this slide here. Oops. Yeah, so what Bros, Epstein, and Glasser established was crossing for 2 to 2 for the non-perturbative amplitude at a fixed momentum transfer t less than 0. And what they showed was basically what's summarized in this picture, that if you have the on-shell S matrix in the S channel and the on-shell S matrix in the U channel, then there exists a path of analytic continuation. Basically, if you take a large enough arc in S, there exists a path of analytic continuations between the two of them. I should say that for the crossing of relations that we were driving, we have not proven them. We kind of took a different route. As I say, these are very technical proofs and very important ones, and we're going to that route for higher points. But for higher points, basically, analogous things have not been proven. What we wanted to do was to first just establish what the crossing relations are, test them out in a bunch of examples, see that they really make sense, and then the next question is precisely if there are any subtleties, when would the proof hold, and if there are any subtleties, or if we can always do this, say for stable particles, etc.
I see. Okay. Thank you. And also in the next slide, I think you had this picture with the 5 points.
Yeah.
So, the next may be similar, that picture similar to this one. Sorry. So this one, right? So here you say that this is going to be the analog of Ross-Epstein Glasser, right? For the 5 points. Now the right hand side should be thought of as electron and photon as incoming particles, right? And 2 electrons or positron coming out as outgoing particles. Now, if I do one single analytic continuation, meaning I guess analytically continuing one particle, right? Then I don't quite land up on the left hand side, right? I would land up on, that positron going back and becoming electron, for example, or one of the electrons will still be a scattering amplitude, not this.
That we don't know. That we actually don't know the answer.
Just from this time-fold kind of picture. So what you have on the right-hand side is 2 guys inserted on the left and 3 guys inserted on the right. And now if I'm allowed to move only one guy, I guess you could move it in the folded way. So
it's that you bring up actually an excellent point, which I didn't have time to talk about, but since you ask, let me mention it. So we proposed this one path of analytic continuation that basically uses the retarded product as a motivation to exchange particles. And what we get is that we get these families of observables that have been analytic continuation between each other. So here I've drawn at 6 points, there are 3 different families. And basically, if we know one thing in this family, let's say I know the S matrix, then I know all of the other ones.
Right.
And what you're asking is what happens if we do something different? What happens if we just cross one particle, for example?
So that's what I was going to. So these arrows are moving one particle, or what are these?
These arrows are always exchanging 2 particles. So we actually have a proposal, we have a conjecture for what happens for multi-particles if we cross many particles with each other. And then you can do a series of moves and get back to maybe crossing one particle. But let me just say for now that it's still an open question whether there are other analytic continuations similar to these ones that would give you something different and that would maybe even connect the different families.
Okay.
So, it's a great question, but it's an open question. We don't quite know what happens.
Nice. Thank you. I mean, as Shiraz was pointing out, in position space, I mean, as you said, there are subtleties to momentum space, but in position space, at least conceptually, things seem clearer.
Yeah, exactly. As I say, the problem is that we know of examples where that doesn't translate into some nice properties.
The path shuts off somehow.
Yeah.
As you go asymptotic.
Yeah.
Okay. Thanks.
So, sorry, just to follow up on that. Yeah, just to follow up on that, you're saying so in position space the analytic continuation seems easier, but are you saying that it's not clear how to go on shell in some sense and get the and that poses a problem, right? But if
yes,
let's say
it's here basically. Yeah, so basically what can happen, for example, let me just say this schematically, but it might be, for example, that the inclusive observable lives down here between the yellow branch cuts. And if we're off shell and we can do this, it's a simple example, it's a triangle example. We can do the crossing off shell. We can take this blue path that gets us between the two branch cuts. But then if we go in the on-shell limit, in this case, then S star basically goes down to the real axis and we just close the region where we need to go for the analytic continuation. So
I see. What does that happen? Sorry.
In the on-shell limit in this case.
Oh, nice.
Yeah, we have an analysis of this. It's
interesting.
Yeah, it's basically if we're crossing a massive particle and we have a massless particle in the loop, then basically this retarded product might not be such that 2' is genuinely in the future and the fastest moving particle, because basically the massless particle moves at the speed of light, but we need this retarded one to be the fastest one by our derivation. So as I say, it's expected from axiomatic field theory, but it also shows that these limits are not, it's not like you can do something off shell, it's not like you can manipulate things in position space, and that will hold for the S matrix.
And if you swap a pair, that always is possible. There you don't have this obstruction. That's why you had these pictures. Is that the case?
Yeah, so if you swap a pair, either with, I guess either with a mass cap, or if you swap a pair with a massless particle, then you're always fine.
I see.
So there can be subtleties, as I say, if you have this, basically if you have a massless particle that can go faster than the massive one, then you can't boost the massive one enough to catch up with it. So yeah, we don't expect this to happen if we have a mass cap, which is what was used entirely in the 60s. And we also don't expect this to happen if our external one was massless, if we measure an external one that's massless. So we have this handle on the analyticity properties, but we haven't, of course, there's many more things that you can imagine doing. You can imagine other time orderings, other forms of retarded or some folded time contour products. And yeah, I think it's a super interesting direction in open questions of how much mileage we can gain.
I have a naive question. Since you have talked about black hole scatterings, how does it pertain to the LIGO experiment? Because there you don't have a scattering. You just have two black holes and coming and forming one single black hole, right?
Yeah, so these have not yet been measured at LIGO with a precision. Let's go back here. Yeah, so LIGO has not reported any measurement of this, but maybe in the future. As I say, it's not really clear. People say a bit different things about when this could be measured. And one of the interesting directions is to try to, as we were talking about earlier, see if we can relate the scattering waveform to the bound state waveform. That would be really a fantastic thing to do, because then we could use all our machinery directly on the LIGO data. So yeah, this would be, there's a difference basically between the scattering waveform and the bound state waveform.
Okay, great. If there are no further questions, let's thank Hofie again for a fantastic talk.
Thanks again for coming.
Thanks so much for the fantastic talk and for your patience with us, Hofie.
Oh, no, it was great. Let's see, I can't, have I stopped sharing?
Yes.
Yeah, okay.
Bye.
Bye.
Bye-bye. See you later.